So I went into the Canvas site and sort of rearrange things a bit. Just kind of cut off the last chapter to slow down. And this week finish. Well, at least I think we actually finished this. That's part of the semester. Let's go through quadratic number fields. Kind of sad. I mean, there's a really cool result that I wanted to get to at the end on fields constructability of certain polygons. It's really beautiful, but I don't want to rush it. So I learn about that. So I did want to kind of give this sketch that I started last week about the fundamental theorem of algebra. I think it's intuitive proof. There's some kind of theorems that you might need that we can't quite do here, but they're pretty reasonable, I think. We just repeat statement and then kind of where we were with it. Algebra says that if F is a column of coefficients, complex numbers, and let's say it's a non-constant, then there's root. There's alpha. C is so the history of this is like pretty long. People thought this was true for a while, and I think the first proof that is where people said, okay, it's proven was with Gauss. Gauss was like a really, was quite as sloppy as I am, but he was pretty sloppy kind of. He didn't seem to care about proving. There was a certain point in math where mathematicians started caring a lot about proving. But I think Gauss was not quite at that generation. He cared about reasoning things out, but like super logical proofs, it wasn't as important. Just like that's true. Come on. At least that's the impression I get from reading about his work. All right, so this is this proof sketch. And what I started with was maybe a sense as to what complex arithmetic looked like. So arithmetic, very geometric. We said that if I have if I have addition by some complex number, say by A plus B, it's like translating by vector if you want, and then multiplication I plus bi, well, we can represent this complex number quite rigorously as in the form of r times e to the I theta in polar coordinates. It's like rotating counterclockwise. say rotating by theta, dilating by r. And so then I wanted to say, what is the operation? To kind of rush to the end. But so what is function c going to z? What does it look?
Scaling by a to the n and then rotating by b times n. Or not, and not a to the n, but like r to the n. And scale, and then rotating by a times.
Well, I guess. So one thing about polar coordinates is that they're sort of, they're unique when you constrain your variables, right? But they're sort of non-unique when you don't. So theta is usually required to be between 0 and 2 pi, right? But the thing about this is, let's look at this expression. I'm going to pick up on what you said. But let's take this and it's r to the n. So indeed, the sort of factor out front will go to the power n. We have e to the n theta. What I was just saying about theta being between 0 and 2 pi, you see here is that if it's like, say, pi and n is 100, now you've got like 100 times pi. Right? So now you're outside of that usual polar framework. It's really gone too far. It's okay. You can go far. You can do what you want, right? So you're certainly right in that the scaling factor are sort of the radius that you're at. It's really taking a power. So here I'm going to assume that n is a positive integer. I don't want it. Fractions, this is kind of complicated for fractions. Can get very complicated. Let's say assume that n is actually a very large number, or just some natural number greater than 0. Let's say n. Let's do that. So let's, ignoring this factor, let's say r is 1. What happens here? So what about r is 1? R is 1, we've got a unit circle. All the complex numbers that where r is 1 is just a unit circle. Right? So the only parameter that matters there is the parameter that's just theta. Theta is going to be this angle. And what am I doing with theta? I'm multiplying it by n. Well, when theta is 0, nothing's happening, right? 0 times n is 0. But when theta becomes, like, say, 2 pi over n, what happens? Just go all the way around. So let's say we divide this up into sort of n, let's say n was 8, for example. Divide this up like a piece of n is less nice one. Okay. And what happens here is that this sector, or this arc, will go all the way around. And then this arc will go all the way around again. Basically what you're doing is you're taking this circle and you're wrapping it around 8 times. That's what you're doing. That's what this function looks like just on the unit circle. But what it looks like away from, like let's say r is big, is it looks sort of the same. It's just now r is going, your radius is also going really far out. And blowing up your radius. and then you're wrapping around. So the way you want to imagine this is you want to imagine sort of, if for r greater than 1, greater than or equal to 1, dilate. I mean, it's true for r less than 1, but that's going to shrink down. So let's just kind of consider scale, you know, I guess we can say scale by r to the n minus 1 because we've got an r factor in front of it. And wrap around n times. Take the single circle, wrap that circle around n times. That's the picture. Okay, so this is what this looks like. And now I want to say, okay, let's look back at the fundamental theorem of algebra. Let's assume, so we'll assume that f has a particular form. Let's say a naught, a1 times z, dot, 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 all the way plus an times z to the n. And what we can say is that, in fact, let's assume that f is monic. There's nothing wrong with f being monic, right? Because certainly for the fundamental theorem of algebra, we're just looking for a root. So if we divided it by a to the n, or a sub n, we'd still have a root. Right? It's not bad. It's just not. So we have some polynomial that looks like this. And what I want to say is for z really big, it's the modulus of z, meaning sort of the radius, order of the radius. So we're saying it's really very far away from the origin. F of z is well approximated by just z to the n. It's dominated by its highest order term. Dominated by its highest order term. It's that sort of the distance here between this function f of z and z to the n becomes very small relative to the size of z as z gets big. Let's say we believe that. In particular, now what do I want to say? Now I want to say the following thing. Now let's say, suppose the fundamental theorem of calculus is false. Fundamental theorem of algebra is false. I suppose fundamental theorem of calculus is false. Yeah, it's hard keeping this and out 3 at the same time. So f of z equaling 0 has no solution. But then f of z, or, sorry, f will send c as a function, polynomial, if I just take the inputs, and it will output this to c star continuously. Polynomials are certainly continuous. I'm going to have to at some point draw a picture, but I'm not quite there yet. Well, I think I might be pretty close. So Yeah. C star is, so this is the same notation we use for any field. It just means all of the numbers minus 0. So because I'm assuming that this has no solutions, so nothing is sent to 0, so I can stay away from 0. So now here's what I want to do. So now I want to consider R times, I'll call it C. I'll consider varying D4 from R big to R big to R. For C is the unit circle. Draw a picture here. Not hard to draw this picture, right? Okay. Here's R big. This is a unit circle, really big, and I'm going to start there, and then I'm going to vary it until it's very, very small, until it goes to, well, notability won't let me, but I'll take it all the way down to a point. That's R0. So this is my RC. Let's say capital RC, this is big. R is big. Then, you know, it's and then we'll take it all the way down. Well, imagine R is varied, lowercase r is varied. What we're going to do is we're going to put this into F. Put this into F, and we're going to ask a question. Let's do that. So I already said consider varying this and double consider F restricted to RC. So when R is equal to capital R, it's really big, our big circle. You know that F restricted to capital RC looks like C to the N restricted to RC. That's how it looks. And our picture, our little cartoon of this is the following. Here's the complex, here's the image. So F is, we know that the cartoon looks like this for Z to the N. It says this goes around N times. Right? But now F is not exactly Z to the N. It'll look like it. So what it'll look like is some kind of, you know, and this is just a sketch, it'll look like something like, you know, it won't exactly overlap, it'll kind of, if N is 3. It's close to Z to the N, but it's not exactly. Now let me put, this is where it becomes more of a, I mean, there's legitimate math beyond this, so I'm not lying to you guys. Let me put like a peg in the complex plane, right? Let me consider this image like a rubber band. Have you guys ever like seen these, like, I don't know, like these pegboards and you put rubber bands on them and stuff like that? Okay, imagine this, but imagine just one peg and the rubber band sort of free floating and you wrap it around however many times. Now what happens when I consider my considerations here? When I vary this circle to this circle, all the way down to 0. What happens is this rubber band, it starts deforming. I can't really say exactly how, but it starts going around, right? It starts deforming. But once I get to 0, that rubber band is now collapsed to a single point somewhere. f of 0. And this whole process is continuous. And that's a problem. Because if you take that rubber band and you try to stretch it to a point, it will snap at something. It gets cut or caught on that run, on that peg. Or have the continuity. And this is actually a theorem in algebraic topology, like almost a fundamental proof. But it's a legitimate theorem that you cannot do this. You cannot contract this. So that's not possible. So the point is that this is not possible. You can't actually have deleted this 0 and this continuous deformation. This is where you get a contradiction. So at r equaling 0, I'll just write this down. RC goes to a point in the f of 0. We get a contradiction. Really to the continuity of this process. It's this being continuous deformation. And this is always the case with these proofs, is that there's always some part of it that relies on some topological or geometric thing about the complex number. There is a Galois proof, but I think even that you can need a little bit of analysis or something. So that gives us the fundamental theorem. That's okay. There must be some 0 here, which means there must be a solution to this. This is I mean, I would say this is certainly out of all the sort of fundamental theorems, this is by far the hardest theorem to prove. Way more than like fundamental theorem of calculus or so. And it took a long time, and I think it was really, but the fact that the complex numbers enjoy this property is not a small thing. It's a very, very, very good thing for a lot of mathematics, very helpful thing. Without it, a lot of things are just not true or impossible to state. And so it's quite nice. Okay. Questions? In fact, there's a property we call field. We'll say that a field is algebraically closed if it satisfies this this property that any polynomial coefficients in that field. All right, so I'm going to return. This is sort of an aside from our project, but I think it's important that people at least see it. Of course. So I'm going to return though to Artin and section 3, 12, chapter 12, where I'm going to try to kind of say what he's doing. This is kind of, there's a lot of lemmas and theorems and so on, a lot of proofs. And I think it's easy to kind of be like, why do I care about all of this? Or why does Arden care about all of this? Like, why does anyone care about it? What's the point? And it's a part of like this process that we're in, where we're trying to understand factorizing in rings and primeness and irreducibility and so on. And there was a Homer problem of them from this section that I went through in the problem session. And this is really about sort of an interplay between looking at Z of X and Q of X. I tried to make it a point of it in the problem session, but I want to kind of reiterate it. This ring, we know now, is because Q is a field, we know that this is a PID and more generally, I mean, it's a Euclidean domain, a PID, and a UFD. So that last one is the sort of thing we were most interested in getting to, is that any PID was a UFD. So we have that this is a UFD. This ring is understandable as far as rings go. Very understandable. This ring, at least on first sight, and maybe second or third, can be much more difficult, right? It's actually much more complicated, and that's because this is not a field. The integers do not form a field. So that makes a lot of things more subtle about this ring, but it raises a question. Which is, let's say we have a ring R. What can we say about, and let's say it's commutative, Rx? So while this ring is complicated, and so is this ring, this ring is maybe less complicated because we do know that that's also Euclidean domain. It satisfies the fundamental theorem. And in particular, it's a UFD. So there is kind of a general question you could ask, which is saying, let's say I have a UFD, and I consider polynomials with coefficients in that UFD. Is this a UFD? Do I still have unique factorization? Do I still have the fundamental theorem of arithmetic if I just consider polynomials with coefficients in that ring? That, I think, is actually kind of a natural question, because you want certain constructions with your rings. You want to be able to say, okay, I have something, I make something else. It's richer, it tells me more information, I can play with it. What properties stay and what properties leave? What do I lose when I make this construction? In this case, there is a general theorem that says if R is a UFD, you still have a UFD. Divides that property. That's really nice. That's very helpful. It's helpful in a lot of different areas. It is not the case if I take a UFD and I quotient by an ideal, consider a quotient ring, that I still am a UFD. Then you lose everything. Then life becomes really hard. Much more subtle. So some constructions, they do not preserve this property, and some constructions do. This is one. So this whole section is about basically going through this exercise with the integers. But actually the proofs are very close in general. You can kind of prove this general statement looking at most of, I think almost all. I think if you, well, okay. There's one theorem that's maybe missing. But a lot of what you need is given in this section for this chapter. Questions about that? But we'll embark on this project then. You guys should interrupt me if I throw a few questions about it. I'd say anything silly. All right, so let's start the lemma. So this is one of the main tricks here, which is when you're in the integers, although this again, you could do this for a PID in general, you can do a lot of tests with your polynomial by sort of reducing modulo some ideal. Let's suppose I have some polynomial f of x, and I'll write it out. Coefficients here. Let's say this guy is integer coefficients. And let's suppose that P is a prime. And the following equivalent. 1. P divides I. P divides F. 3. Okay, so I'm going to write down what's in the text, but okay, F is in the kernel. I'll explain. Kernel of this map. This is a homomorphism size P. What it does is it takes all integer polynomials, sends them to polynomials with coefficients f of P, where you're just reducing the integer mod P. You're reducing the coefficients mod P. This does give a homomorphism based on one of the early theorems we've had on homomorphisms. Let's reduce your coefficient. All right, so let's do a gut check, and you guys can help me with this. So what do we do when we have a following our equivalent type? Right, so start with 1 and imply like 2, maybe. I want to like go around in some circle here. Okay, so how do we show this? Right. This is a sort of a direct proof, right? So by 1, AI equals P times BI, or some integer BI. So let's write it down. So f of x equal to an x to the n plus dot 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 a naught equal to p times dn x to the n dot 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 plus naught. What do we do now? Factor out p. P times dn times x to the n. P divides. What it means to divide, right? It's one of the equivalent ways of thinking about divide. Okay, so that wasn't yeah. So that 2 implies 3.
If you have that P factored out like we do, mod P of P is going to be 0, so we're multiplying something by 0, so it's 0.
Right, very good. So if f, let's write it out though. F of x equals times g of x. Then, okay, so this, I'm going to write this down. So this function size of p has notation. If I have f to be sent to, you put like a bar over it. Just to note that that's its image in here. It's mod. You're modding out the coefficient. That's just easier than having to kind of right size everything. And f of x are g of x, but this is a homomorph. G of x and this. Mention this is 0. 0 times something. So it's in the kernel. All right. More. Everything you said is true, but I think the most direct route is to actually, I mean, everything you say is okay. But I think because it's just sort of, actually what you said, I think it's faster to go, you're giving a 3 implies 2, a quick one there, which is very much equivalent more or less, but I want to go all the way to each of the AI. So what I would do instead is just is go ahead and write it down. So say, okay, then 0 is equal to f of x. And I would expand it out. And x to the n. Sorry. This part here. And then I've got this I mean, the way you actually define this homomorphism is just reduce the coefficients. But then I can see individually for each coefficient rather than all at once. Pi, which is equivalent. This is mod p. That means that p divides all. That's it. Okay, so this is one of the tools if you're playing with, actually, if you're playing with a polynomial with coefficients in a PID, this is sort of a constant. This is something you do a lot. You kind of can reduce modulo some irreducible or some prime. So now what we want to do is we want a definition that will allow us, that's sort of like monic, but it's a little more refined. That'll allow us to sort of reduce, or well, get an interplay between polynomials in Q of x and those in Z of x. So here's the definition. We say f of x, Z of x, primitive, if coefficients, let's say if it's non-zero, 1 and 0, its coefficients are relatively prime. There's no common factor, that's what we need. And the leading coefficient is positive. In a sense, this is, well, then you can really rewrite this lemma well, I'll just say it. I don't want to rewrite it. So with this notion in mind, we can kind of rewrite this lemma as the following. So with the new notation, we can say we could say like f is primitive. It's not exactly a rewrite, but it's sort of the same. It's something you can do for using this lemma, you get a new lemma. F not divisible by p, all p, all prime p. And 3, the This is just saying that f is never 0. Sort of the, it's the negation of all of these three things. All. But there's kind of a lemma. This is a different lemma, but it follows immediately from this one. I want to at least prove Gauss's lemma before we finish, which is sort of a key proposition. Sorry. Let me move on. I don't really care about that lemma very much. 12.3.4, 12.3.4. One, or A here is as an integer prime t of x. So that you can only okay, and then B is but it's silly, but actually it's kind of the main point of Gauss. That the product of primitive polynomials which okay. That actually is not intuitively obvious. That's where this is sort of like everything on its by itself in steps is kind of obvious, but then if you were to like skip all of the steps and you just wrote that down and you said, hey, try to prove that, it might be a little hard. You're saying none of this is obvious. What are you talking about? If you've read this, like, taught this kind of a course, 4 times, this becomes very obvious. All of it. Yes.
When we're saying the coefficients are relatively prime for primitive, do we mean like each coefficient is relatively prime to every single other one, or just like you can't
collectively, they don't have a common factor.
Between the two primitive polynomials, if you're multiplying them, do they have to be relatively prime to each other as well? Or
no, they can. They're just any two primitive polynomials in the world. Take them, take their product. That's a primitive polynomial. Why is that kind of? Why would you not? Why do I not think that's obvious on its face? Because polynomial products is not the most naive thing in the world. It's not the most elementary thing, right? You have these. Sure, the leading orders are just multiplying, but everything in between, you have this big sum of products. And so it's like, I don't know, like maybe you create a factor when you add all of these things up. So it's not immediate at all at this time, but it follows from what we'll do right now. So let's do A first. So what does A say? So A says if P is, well, one direction today says if P is prime in C, then and P divides the product of two polynomials, f of P, to integer polynomials, then P divides F, using the notation again, guys. Divides F for G. Okay. Okay. Well, what do you think? I mean, the converse is, it should be obvious, right? If this holds, if this implies this in polynomials, then it's certainly prime in Z, because you can just take constant polynomials here. So one way is up, yeah.
So we could use like the lemma and say that we have two, so P divides some function Z of X, then divides all the coefficients.
Okay, yeah, use the lemma. So let's use lemma. How do we use the lemma? It's good. Right. Let's look. We're assuming this, right? We're assuming that P divides this product here. But since P divides the product, we have that F times G is 0. P. That's the third part of that one. Look at this. So the homomorphism. F is a field. F sub P is a field. Like two things, the product is 0. What does that mean? Fields are integral domains too. One must be 0. So in particular, this is an integral domain. F is a field. This is an integral domain. I mean, it's a PID, so it's a domain. Let's say that F dx is domain. F equals 0 or dx 0 divided. That, again, using the lemma, we have an equivalence between f of x equaling 0 and f tx, and P dividing. Lemma. Either P divides f or P divides g. That's A. I mean, as I said, the other version is obvious. I mean, if P is prime in Z of X, then taking constant polynomials shows that P is prime. Okay, so how do we use this? Well, this is this other version of the lemma you can use to say, okay, so for Gauss's lemma, we just say, okay, so suppose f and g are primitive, then the coefficients of f times g, I'm just leaving off the x now, are relatively prime. Why is that? Because if they weren't, then there would be some prime that divided all of them, right? And then P would divide by A, divides F or G, right, by A. but they're primitive, so they keep. Right. The coefficients of F or the coefficients of G are all relatively, so they can't. Okay, and then the other condition is just the leading coefficient is positive, but clearly the leading coefficient is the product of the two leading coefficients, so they're both positive. That's basically. All right, guys, we'll continue on Wednesday.